Hello everyone, this is Stuart Mason with another Math 156 script. Today we're doing 5C, max, min, and median.r. So we're still talking about sampling statistics and sampling distributions. We're introducing three new sampling statistics, the max, min, and median of a sample. These three are special cases of the more general idea of order statistics. So basically, you take a sample, you arrange them in order least to greatest, and then you can make inferences about the probability of the nth one of those being what it is. So in this case, the minimum is the first order statistic, the maximum is the nth order statistic, and the median is the central order statistic. So page 83 of the textbook has a nice formula for order statistics in terms of the cumulative distribution function and the probability density function. Depending on the distribution in question, that may or may not have a nice closed simple form. Fortunately, computers let us circumvent this problem of having a nice closed simple form. That's what we're going to do in this script, and all the examples really follow the same sort of pattern. So we're going to start off with a uniform distribution on 0, 1. This is also known as the standard uniform distribution. And we're going to be taking 10,000 draws from this distribution and storing the max, the mins, and the medians. So this is just a trial run to get you acquainted with the concept. We're using the RUnif function. As always, if you want to know what a function does, call up the help. So this is functions surrounding the uniform distribution. R is random draw. The first argument, n, is the number we want. And by default, its range is 0 to 1, which is perfect. So if we just run that, we get some values in x, and we can store the max, min, and median. Let's do this 10,000 times, storing the results. And take a look at the resulting approximate sampling distributions. Okay, so you see it's very unlikely that our max is very small, and it gets more and more likely that our max is larger. Now, in the case of the uniform distribution, the order statistics do have a nice closed form, and that's what we call the beta distribution. The beta distribution comes a lot when you're estimating probabilities because it always takes values between 0 and 1. So in this case, we're using the d beta function, as in density beta, to draw the curve for a beta with these two parameters. These parameters are determined by how many samples you've taken and which order statistics you're interested in. There's a formula on Wikipedia you can look up if you're curious, but we'll just take Paul's word for it here. And you see it nicely approximates the histogram. We can also use the formula from page 83. This is going to be our general strategy for the rest of the script. So the max order statistic is n times 1 minus the cumulative distribution function to the power n minus 1 times the density function. And you see it nicely overwrites the theoretical value. And the mean is going to be our estimate of the center of this distribution, or the expected value of the third order statistic, which Paul tells us the theoretical value is 3/4. And this should be nice and pleasing. If you draw 3 samples from a uniform distribution between 0 and 1 and put them in order, you'd expect most often for the first sample to be around 0.25, for the second sample to be around 0.5, and the third sample to be around 0.75. And you'll see that's exactly what happens. Now let's do the minimum. And again, these parameters are determined by the sample size and which statistic we're interested in. There's the curve. We can overwrite it with the explicit formula and take the mean. And here we have, see, very close to 1/4. Again, that makes nice intuitive sense. The median is a sort of different shape, but again, it's clustered right around what we expect, and the histogram and the curves all nicely agree with each other, and the mean is right around 0.5. Okay, so now we're going to be doing an exponential distribution for lambda equals 1, and again, this really isn't anything new. It's the same basic idea as before. We use a for loop to store each of these values 10,000 times. We can look at the distribution of the maximum. And again, we're using that formula from page 83 to explicitly write this. And we can take the mean to get an estimate. Paul points out this is probably a challenge to calculate. I haven't even tried. I think this one probably has a closed form because these exponentials are nice and easy to integrate. But we just don't need to. And here we'll do the mean. Here we'll do the minimum. And the median. And this should be clustered right around 1, because we know that this is a lambda value of 1, so the expectation should be 1. And finally, we're going to be doing it for a normal distribution. This time we'll be doing it with 7 samples. So we'll be taking R norm 7, this is random normal 7, and you'll recall if you don't feed it any other parameters other than the number you want, you'll get a standard normal, so mean 0, standard deviation 1, and we'll store the max and the min. We can take a look at sort of where the maximum lies. It looks itself somewhat normal, although it isn't quite. Then again, the more samples we take, the more normal it becomes. And we can draw the curve. I'd say this thing isn't quite normal because keep in mind, its probability distribution function will involve both the cumulative of the normal and the density of the normal. When you multiply those two things together, the density doesn't even have a closed form, so you're certainly not going to get something with a nice closed form like the normal has. Paul wrote maximum here, but he meant minimum. Oh. And again, you see this one has a bit more of a skew to it, but using the formula we get a nice approximation. So this is sort of a very generalizable idea of sampling distributions and order statistics with a couple of visual examples. I hope this was helpful. As always, send any questions to smason@post.harvard.edu, and I'll see you guys on Wednesday.